This is an audio recording for visual impaired student from Pradeep's Organic Chemistry Volume 1 by Dr. S. N. Dhawan. Chapter 3 Stereochemistry of Organic Compounds. Introduction. One of the most important characteristics of organic compound is their ability to show isomerisms. Isomerisms are the compounds which have the same molecular formula but different chemical and physical properties. It is of two types, structural isomers and stereoisomers. Structural isomerism. Compound having the same molecular formula but different their structure. Different arrangement atoms within the molecule are called structural isomers and the phenomena is called structural isomerism. It is of six types. Chain or nuclear isomerism. Compound having the same molecular formula but different arrangement of carbon chain within the molecule are called chain or nuclear isomerisms and the phenomena is called chain or nuclear isomerisms. For example, C4H10, butane and 2-methyl propane or isobutane. Next, position isomerisms. Compound which have the same structure of carbon chain but differ only in the position of multiple bond or functional group are called position isomerisms and the phenomena is called positional isomerisms. For example, but1-ene and but2-ene. Functional isomerisms. Compound having the same molecular formula but different functional group are called functional isomers and the phenomena is called functional isomerisms. For example, the molecular formula C2H6O represent the following two functional isomers, ethanol and methoxymethane. It may however be noted that orthocresol, metacresol and paracresol are themselves positional isomers. Metamerisms. Compound having the same molecular formula but different number of carbon atoms, the other side on the functional group, are called metamers and the phenomena called metamerisms. Metamerisms occurs among the member of same homologous family. For example, ethoxyethane is a metamer of 1-methoxypropane and 2-methoxypropane. Now tautomerism. It is arises due to 1,3 migration of hydrogen atom from one polyvalent atom to the other within the same molecule. Isomers thus obtained which exist in dynamic equilibrium with each other are called tautomers and the phenomena is called tautomerism. For example, acetaldehyde is a tautomer of enol form or vinyl alcohol. Ring chain isomerisms. Compound having the same molecular formula but possessing open chain and cyclic structures are called ring chain isomers and the phenomena is called ring chain isomerisms. For example, C3H6, propene and cyclopropane which are ring chain isomer. Double bond equivalents. Double bond equivalent is called index number of the index of hydrogen deficiency. The problems of structural isomers and structure determination of organic molecule can be easily solved by the concept of double bond equivalent, which implies the sum of double bond and rings present in the molecule. It is given by relation double bond equivalent is equal to sigma n into V minus 2 upon 2 plus 1, where n is the number of different kind of atom present in the molecule and V is the velocity of each atom. Stereoisomerism. Isomers which have the same structural formula but have different relative arrangement of atoms or group in space are called stereoisomers. Greek word is stereo and it means space. Merso means part and the phenomena is called stereoisomerisms. Stereoisomers are of following two types, conformational isomers and configurational isomers. Stereoisomers which differ in the relative position of atom within the molecule and which can be interconverted simply by rotation about sigma bonds are called conformational isomers. Configurational isomers, stereoisomers which can be interconverted only by breaking and remarking of covalent bond and not simply by rotation about sigma bonds are called configurational isomers. These are of the following two types, optical isomerisms and geometrical isomerisms. Optical isomerisms. Certain compound can exist in two stereoisomer form which cannot be superimposed on one another. In spite of these differences in the relative spatial arrangement of atoms, these isomers have identical physical properties such as melting point, boiling point, refractive index, density, solubility, etc. They have resemble one another in most of their chemical reactions. However, they differ only in their behavior towards plane polarized light. One rotates the plane of polarized light toward right but other toward left but to the same extent. Such a pair of compound are called optical isomers and the phenomena is called optical activity. Some general concept about optical isomerisms. Plain polarized light. Ordinary light consists of electromagnetic wave of different wavelengths. Monochromatic light, on the other hand, consists of waves of only one wavelength. It can be obtained either by passing the ordinary white light through a prism or grating, or by using a source which gives light of only one wavelength. For example, sodium lamp emit yellow light of about 589.3 nanometer wavelength. Such a beam of light which has vibration only in one plane is called plane polarized light. The nickel prism used to obtain plane polarized light is called polarizer. Angle of rotation. The angle through which the plane of polarized light gets rotated on passing through the solution of an optically active compound is called angle of rotation. It is denoted by Greek letter alpha. Polarimeter. The instrument used for measuring the angle of rotation of a plane polarized light is called a polarimeter. It consists of light source, two nickel prism and a polarimeter tube. The nickel prism near the light source is called polarizer, while the near the eye of the observer is called polarimeter. Now, the angle of rotation alpha of an optically active compound depend upon following factors: nature of optically active substance, concentration of solution in gram per milliliter, length of solution through which the light passes, nature of solvent, wavelength of monochromatic light used, temperature of sample. Specific rotation. In order to compare the rotatory power of different optically active substances, the optical activity is usually expressed in terms of specific rotation. The specific rotation of an optically active substance is defined as the degree of rotation observed when the plane polarized light is passes through a tube having a path length of 1 decimeter and a concentration of 1 gram per milliliter of the compound at specific temperature and wavelength. It is mathematically calculated as alpha capital D to small t is equal to observed angle of rotation alpha divided by L into C, where L is length of polarimeter tube in decimeter and C is the concentration of substance in gram per milliliter. Optically active activity discovery. The phenomena of optically activity was discovered by the French chemist Louis Pasteur in 1848. Such substances which can rotate the plane of polarized light are called optically active substance, and the property of substance to rotate the plane of polarized light is called optical activity. A substance which rotates the plane of polarized light toward right is called dextrorotatory, and which rotate toward left is called levorotatory. Chirality. An inspection of the molecular structure of optically active compound indicate that all these compounds have chiral or dissymmetric molecule. A molecule is said to be chiral or dissymmetric if it is not superimposable on its mirror image, and a property of non-superimposability is called chirality. On the other hand, a molecule which is superimposable on its mirror image is called achiral. Molecular chirality and asymmetrical carbon. Such a carbon atom which is attached to four different substituents is called asymmetric carbon atom or chiral carbon atom, or simply chiral center. A chiral carbon atom is indicated by asterisk. Further, it can be noted in the carbon which make the molecule dissymmetric or chiral as explained below. Element of symmetry. The superimposability of an object and its mirror image can be tested with the help of three elements of symmetry, such as plane of symmetry of or center of symmetry or alternating axis of symmetry. Chiral objects do not have an element of symmetry. On the other hand, chiral objects have at least one or more plane of symmetry. Plane of symmetry. The most common observed element symmetry is plane of symmetry or plane or sigma plane. It is defined as an imaginary plane which divides the molecule into two equal halves such that one half of the molecule is a mirror image of other. Center of symmetry. A center of symmetry is defined as the point from which line which drawn on one side and produced on equal distance on other side will meet identical points is called center of symmetry. Alternating axis of symmetry. A molecule is said to be possess an unfold alternating axis of symmetry if rotation through an angle of 360 upon and about this axis and then followed by reflection in a plane perpendicular to the axis, gives a molecule which is indistinguishable from the original molecule. Relationship between asymmetry, dissymmetry, and chirality. It is interesting to note that while describing optical activity of organic compound, two terms asymmetry and dissymmetry have been used without any distinction, yet there exists a subtle difference between them. A molecule which has no element of symmetry is called asymmetry molecule. Such a molecule is usually optically active. On the other hand, a molecule in which no alternating axis of symmetry but may or may not have a simple axis of symmetry is called dissymmetric molecule. Like asymmetric, dissymmetric molecule are also usually optically active. Stereogenic center or stereocenter. We have noted that a tetrahedral carbon atom attached to four different atom or group are called asymmetric or chiral carbon atom. However, in 1984, K. Mislow and J. Siegel pointed out that use of them term chiral carbon atom has created conceptual confusion. According to these scientists, it is not the atom which is chiral, but actually it is the molecule which is chiral. In other words, chirality is a geometric property which prevails, extends, and affects all pair of chiral molecule. For example, all the atom of 2-butanol are in a chiral environment, and hence all are said to be chirotropic. Thus, all the chiral centers are stereogenic, but all stereogenic centers are not chiral centers. Therefore, in this unit, hence after we shall use term stereogenic center instead of chiral center. Configuration and Fischer projection. Stereoisomers have the same molecular structure but different relative arrangement of atom or groups in space. The spatial arrangement of atom or groups which characterizes or defined a particular stereoisomer is called configuration. The configuration of organic molecule can be best visualized by inspection of their models of three-dimensional structures, depending upon how you hold the molecule of three-dimensional structure organic compound. In this model, three types of line are used in flying wedge model: a solid wedge and a dotted line and a solid line. The molecule of any chiral compound containing the chiral center is viewed in such a way that two of group attached to chiral center are horizontal and point toward the observer, while other two are vertical and point away the observer. The various atom or group attached to the chiral center are then projected on the plane of paper form of cross. If the chiral molecule contains two or more chiral center, each chiral center must be viewed individually in the manner of described above. As far as possible, the vertical part of projection formula thus obtained should represent longest chain of carbon atom with the most oxidized carbon, lactic acid, glyceraldehyde. This carbon atom is then numbered according to IUPAC nomenclature. Depending upon which bonds are drawn in the horizontal and which bonds are drawn in vertical position, several Fischer projections can be written for the same compound. A Fischer projection must be not be lifted from the plane of paper and turned over. Such an operation gives an enantiomer of original molecule. For example, structures. A Fischer projection may be turned through 180 degree in the plane of paper. Such operation gives the same stereoisomers. A Fischer projection should not be turned over 90 degree or 270 degree in the plane of paper. Such operation gives an enantiomer of original molecule. One may interchange the group attached to chiral carbon an even number of times in a Fischer projection without affecting the configuration of the molecule. Optical isomerisms. All the optical active compounds exist in two or more isomeric forms which differ from one another in the relative spatial arrangement of atom or groups. These stereoisomers, which resemble one another in their chemical reaction and most of physical properties, but differ in their behavior toward plane polarized light, are called optical isomers, and the phenomena is called optical isomerisms. Optical isomers in a compound containing one chiral center or one stereogenic center enantiomer. This is the simplest kind of optical isomerism and was discovered by French chemist Louis Pasteur in 1848. As stated above, an optical active compound can exist in two or more stereoisomeric form called optical isomers. Optical isomers which are non-superimposable mirror image of each other are called enantiomer and the phenomena is called enantiomerisms. The enantiomers have identical physical and chemical properties but rotate the plane polarized light in opposite direction but to the same extent. Condition for enantiomer. It may be noted that necessary and sufficient condition for a molecule to exhibit enantiomer and hence optical activity is chirality and dissymmetry of the molecule, and its mirror image must be non-superimposable. It may or may not be chiral or asymmetric carbon atoms. For example, mesotartric acid is optically inactive, contain a plane of symmetry and hence does not show enantiomerisms. Properties of enantiomerisms. The important properties of enantiomerisms are they have identical physical properties such as melting point, boiling point, densities, solubilities, refractive indices, etc. They differ only in the direction of rotation of plane polarized light. One rotate in the light toward right and other is left, same extent. Enantiomers have identical chemical properties except toward optically active reagents. Enantiomers have different biological properties. This difference in reactivity of enantiomer of great importance in biochemistry and chemistry taking place in our body. Chiral or achiral molecule with two stereogenic center or optical isomerisms in compound containing two stereogenic centers. So far we discussed that presence of one stereogenic center make the molecule dissymmetry or chiral. As a result, compound containing one stereogenic center can exist in two stereoisomers known as enantiomer. For example, dissimilar stereogenic center in 2,3-dichloropentane and similar stereogenic center in tartaric acid. Compound with the two dissimilar centers are diastereomers. Compound such as 2,3-dichloropentane containing two dissimilar stereogenic center and hence can exist in four stereogenic center which are optically active. Such stereoisomers which are not mirror image of each other are called diastereomers or simply diastereoisomers. Properties of diastereomers. Physical properties: melting point, boiling point, etc. Unlike enantiomer, diastereoisomers have different physical properties such as melting point, boiling point, solubility in a given solvent, densities, refractive index, etc. Separation. Due to the difference in physical properties, diastereoisomers, unlike enantiomer, can be separated by physical method of separation such as fractional crystallization, fractional distillation, chromatography, etc. Behavior toward plane polarized light. Diastereoisomers may be either optically active or inactive. Chemical properties: unlike enantiomers, diastereomers have similar but not identical chemical properties. Thus, the rate of reaction of a diastereomer with chiral or achiral reagent are generally different. Trio and erythrodiastereomers. Molecule of the type RCAB CACR containing two stereogenic centers have been extensively used in mechanical study and special nomenclature have been developed of the system. This nomenclature is based upon the name of two 4-carbon atom sugar, erythros and threose. If if the two like group A in the projection formula are on the same side as two hydroxyl group in erythros, the isomer is called erythroisomer, and if there are on the opposite side of the hydroxyl group in threose is called threoisomers. Optical isomers in compound containing more than two stereogenic center or chiral compound atoms. From the above discussed, it follows the number of stereoisomer depends upon the number of stereogenic center or chiral carbon atom in molecule. For compound containing stereogenic center, there are two stereoisomers. For compound containing two dissimilar stereogenic center, the number of stereogenic center is 4. Working on similar line, we conclude that compound containing n dissimilar stereogenic exist in 2 raised to power n stereoisomers. Prochirality and prochiral molecule. A carbon atom in a molecule is called prochiral if the replacement of one of H atom by a substituent atom or group produce a chiral center. For example, C2 in propanoic acid is prochiral since replacement of one H atom C2 by Br produce a chiral molecule. Molecule which contain prochiral center are called prochiral molecule and phenomena is called prochirality. Racemic modification or racemic mixture. When equal amount of two enantiomers are mixed together, it gives an optically active form called the racemic mixture or racemic modification. It is denoted by using the prefix plus, minus or rs. before the name compound. For example, equal amount plus lactic and minus lactic to mix together. 50% lactic plus 50% minus lactic gives plus minus lactic acid, a racemic mixture. A racemic mixture is always optically inactive because the rotation of caused by the molecule of one enantiomer are exactly cancelled by equal and opposite rotation caused by some number of molecule of other enantiomer. Racemization, the process of converting of enantiomer plus or minus of an optically active compound into racemic mixture is called racemization. By rotation about carbon-carbon single bond, the optically active of ortho substituent diphenyl is due to the restricted rotation about the carbon-carbon single bond joining two phenyl groups. This case of the restrict rotation in presence of bulky substance of ortho position of two phenyl group. These compound undergo racemization on heating. For example, 6,6-dinitrophenic acid or other enantiomer. By enolization, optically active aldehyde or ketones having a hydrogen atom on the alpha chiral carbon from undergo racemization or treatment with an acid or base. For example, acid catalyzed enolization. By SN1 mechanism, racemization of optically active secondary halides such as 2-chloro-butane occur when treated with Lewis acid AlCl3. Under these conditions, the alkyl halide first undergo ionization by SN1 process to form carbocation. By SN2 mechanism, optically active halide having the halogen on the chiral carbon can also undergo racemization of SN2 mechanism. D, L, and RS nomenclature, relative and absolute configuration. The arrangement of atom or group of atom which characteristic a particular stereoisomer is called configuration. By absolute configuration, we mean the actual arrangement of atom or group of atom in space per particular stereoisomer of compound. The relative configuration, on the other hand, means the arrangement of atom or group of atom in space of stereoisomer of compound relative to the atom or group of atom of another compound chosen as arbitrary standard. DL nomenclature. Before 1951, there was no method available for determining the absolute configuration of compound. Therefore, the relative configuration of all compounds were stabilized glyceraldehyde chosen the arbitrary standard. The two enantiomer of this compound was designed by D and L. The plus enantiomer was given the symbol D was assigned in configuration, and on the other hand minus glyceraldehyde was given the symbol L and was assigned the configuration on the OH group is toward left and H right side. RS nomenclature absolute configuration. The limitation of DL configuration system have however been removed by system developed by R.S. Chun, England, C.K. Ingold, and V. Perlog, Switzerland, called Chan-Ingold-Prague CIP system, or simply the RS system. The design by following step. A priority number of such as 1, 2, 3, 4 is assigned to each other 4 atom or groups of atom attached to the chiral carbon in accordance with the following sequence rule. Sequence rule 1. If the 4 substituents attached to chiral carbon are all atoms, their priority number are decided on the basis of their atomic number. The number of higher atomic number get the higher priority. Thus, the compound bromochloroiodomethane, the order of decreasing priority I1, Br2, Cl3H4. If the two atoms attached to chiral carbon are isotope of same element, the isotope of higher mass number of get higher priority. For example, bromochloroiodomethane and alpha deuterioethyl bromide. Sequence rule second. If the relative priority of two groups attached to the chiral carbon cannot decided on the basis of rule 1, it may be decided by comparing the atomic number of the next in the group of the chiral carbon to the first point. Sequence rule 3. Double bond or triple bond double bond and triple bond are treated as if they have duplicate or triplicate single bond. In other words, each doubly bonded atom is duplicated, each triply bonded atom is triplicated. Projection formulae. The atoms group shown below the plane of the paper is kept at the bottom of Fisher projection formula, and remaining 3 atoms are arranged in same sequence, clockwise or anticlockwise, as they appear in the flying wedge formula. Geometrical isomers. Geometrical isomers may also be regarded as diastereomers. Some important examples of these kind diastereoisomers: carbon-carbon double bond. We know that a double bond consists of a alpha bond and a sigma bond and pi bond. The pi bond is formed by sideways overlapping of unhybridized p orbital of two carbon atom above, below, and plane of carbon atom. If now one of the carbon atom is double bond is rotated with respect of other, the p orbital will no longer overlap and pi bond should break. But the breaking of pi bond requires 251 kJ per mole of energy, which is not provided by the collision of molecule at room temperature. Consequently, the rotation about a carbon-carbon double bond is not free up but is strongly hindered or restricted. As a result, many substituent alkene can exist in two distinct isomers which differ from each other only in relative position of atom or group in space around the double bond. Determination of configuration of geometric isomers on the basis of their physical properties. Melting points. In general, the melting point of trans isomer is higher than that of corresponding cis isomers. Solubility. In general, the solubility of a cis isomer is higher than that of corresponding trans isomer. This is due to the reason the molecule of cis isomer are weakly held in crystal lattice than corresponding trans isomer. Dipole moment. Cis isomer have higher dipole moment than corresponding trans isomer. May have even zero dipole moment when atom or group atom on each carbon double bond are the same. Boiling point. The boiling point of cis isomers are higher than those of corresponding trans isomers on the basis of their chemical reaction formation of cyclic compound. The method are more dependable than the physical method. In cis isomer, the reacting compound group being on the same side of double bond interact with each other, resulting the formation of cyclic compounds. E and Z system of nomenclature. We have seen about the cis and trans notation can be used without any ambiguity to describe the spatial orientation of two identical atom or group around a double bond in distinct alkenes. However, in case of tri and tetra substituent alkene, which three or four different atom or group attached to the carbon's atom of double bond, is difficult to assign cis and trans notation. Following the sequence rule describe the optically active compound RS system. A priority order is assigned to the two atom or group attached to each carbon atom of double bond. If the atom or group of higher priority on each carbon atom of double bond are the opposite side of double bond, configuration is designed as E. If on another hand the atom group higher priority on each other atom of the double bond are same side of double bond, configuration the design as Z configuration. Let us now illustrate these rule by following examples. The two geometrical isomers for 1-bromo, 2-chloro-fluoro, 1-iodoethane are cis and trans isomer 2-butene and can be designed Z and E butene respectively. Conformational isomers. A sigma bond between two carbon atom is formed by overlap of sp3 hybrid orbital of each carbon along their internuclear axis. Therefore, the electron distribution within the molecular orbital thus formed is cylindrical, symmetrical along the internuclear axis. The infinite number of momentary arrangement of atom in space which results through the rotation about single bond are called conformation or rotational isomers, simple rotamer. Sauer's formula: the bond between two carbon atoms drawn diagonally is slightly elongated for clarity. The lower left hand is considered to be toward the front of the upper right and carbon toward the back. The Sauer's representation staggered and eclipsed conformation of ethane are shown. Flying wedge representation: in this formula, the bond connecting two carbon atoms are drawn horizontally in plane of paper. Wedges represent bond lying above the plane of paper. Ordinary line are used to denote bond lying with the plane of paper, and dotted lines stand bond lying below the plane of paper. Newman projection of formula. Newman devised a simply and highly useful method representing three-dimensional formula. After his name, these are called Newman projection. These projection formula are obtained by viewing the molecule along the bond joining the two carbon atoms. The carbon atom near the eye is represented by three atoms attached to by three equally spaced 120-degree radii. The carbon atom of the further from I side is a circle and 3 atom or group attached to by 3 equally spaced radial extensions. The Newman projection, staggered and eclipse conformations. Ethane are shown in figure. Conformation of cycloalkanes. Like alkane, cycloalkane also show conformational isomerisms. Cyclopropane and cyclobutane are planar molecules with bond angle of 60 and 90 respectively. Further greater the deviation for strand, the molecule and hence more reactive is very compound. For example, cyclopropane with a bond angle of 60 very strained and hence very reactive. Cyclobutane with a bond angle 90 less strained and hence it is more stable but reactive than cyclopropane. On the other hand, Sech and Moore in 1890s suggest that cyclohexane has two non-planar or puckered conformational called chair and boat conformations. Relative stability of chair and boat conformations. Although both chair and boat form are free from angle strain. In the chair conformation, the carbon-carbon and carbon-hydrogen bonds atoms are staggered with respect to another atom. On the other hand, in the boat conformation, through the carbon-carbon and carbon-hydrogen bond or the staggered orientation, those are in unfavorable eclipse interaction. As a result of these eclipse interaction, the boat form of cyclohexane, in contrast of their chair form, the concentration torsion strain as well as steric strain, although like chair form, it has no angle strain. The boat form of cyclohexane further destabilized by the steric strain between the non-bonded flagpole hydrogen atom. These flagpole hydrogen atoms are separated from each other distance 1.83 angstrom, distance considerably less than the sum of their van der Waals radii. As a result, tectonic cloud of these bonds repel each other, thereby further raising the energy content of the boat form. Other conformations or cyclohexane and their relative stabilities. In addition to the chair and boat conformation discussed above, cyclohexane in principle can adopt many other conformations. Of these, only the twist boat or skew boat and half chair conformation are imported. We'll discuss below. The twist boat conformation can be obtained from the boat conformations. Axial and equatorial bond in cyclohexane. The 12 hydrogen atom of cyclohexane can be divided into two sets, each containing 6 those hydrogen atoms which lie above and below the general plane of molecule and are parallel to the axis of cyclohexane ring are called axial hydrogen atoms, and the bonds holding these hydrogen atoms are called axial bonds. These are usually designed by letter A. The other set of 6 hydrogen atoms which extended radial toward an angle of 109 degree 28 minute to the axis are essentially situated along the equator of the cyclohexane ring are called equatorial hydrogen atom, and the bond holding them are called equatorial bonds. It is indicated by the letter E. Difference between configuration and conformational isomers. The term conformation should not be confused. The configuration although represent the spatial arrangement of atom or group of atom molecule, whereas the various conformation of molecule can be easily interconverted simply by rotation without single bond. The different configuration of molecule can be interconverted breaking and making of bond. A configuration, on the other hand, characteristic a particular stereoisomer of compound. For example, cis-2-butene, the two methyl groups are on the same side of other double bond in the transition trans-2-methyl group, either opposite side of double bond. In other words, cis-2-butene represent a particular stereoisomer 2-butene. Similar, trans-2-butene represent another stereoisomer of 2-butene. The cis-2-butene and trans-2-butene are conformational isomers of 2-butene.